Okay, so let's look at the solution to this problem here. In this problem here, we're going to draw resonance structures for each species, and the resonance structure that we end up with has to be better than the one that I provided here originally. We're going to show the arrows that link the originally drawn resonance structure to the new resonance structure, and then finally we're going to explain why the new resonance structure is better. Okay, so let's look at the first one here. All right, so in the first one, we can interconvert or get a new resonance structure by drawing the set of arrows that I've drawn there. Okay, this gives us 2 lone pairs at nitrogen. So this is now going to have a negative charge, and this is going to be CH2 here. Okay, notice how we have the same number of lone pairs, same net charge, same connectivity, so therefore these two are resonance structures. And why is this one better? This one is better because the negative charge is at the more electronegative atom. Okay, so nitrogen's more electronegative than carbon, and therefore nitrogen could hold the negative charge a little better. Okay, in this one, we can write another resonance structure here where we now donate that lone pair there into making a carbon-sulfur pi bond. Okay, the net structure we would end up with is this one, has a positive charge at sulfur, and this resonance structure that I've drawn here would be superior to the resonance structure above it because it has a maximum number of covalent bonds. Notice that the connectivity is the same. There's a carbon bound to a hydrogen, a sulfur, and another carbon. That's what we have here, but we're binding it through a double bond to sulfur instead of a single bond to sulfur. But these two structures really differ only in the placement of electrons. They have the same net charge. Therefore, that structure down at the bottom would be the better one. Okay, let's look at this one. Here, we can draw a structure where we basically, the arrows go like this. This is, I realize there's more arrows in this one than what you're used to drawing. But this would be the alternate resonance structure that we draw here. And here you can see that the advantage to this resonance structure is kind of obvious. There's no charges. No formal charges. So we could say that this one is better because there's less charge separation. If you're not comfortable doing all those arrows at once, you could do these one at a time, where you would do a resonance structure like this one. Okay, then once you have this one, you could see that there would be the possibility to write another one like that, and that would be ultimately the best resonance form you could draw for that compound. Okay, let's look at the next one. The next one, we're going to designate the strong and the weak acids, bases and acids in this one, and we're going to predict the direction of equilibrium. We're also going to be given the fact that the starting pKa of one of these compounds, the starting pKa is 10. Okay, all right, so this is obviously going to be the acid because it's got a pKa value associated with it. It's giving up its proton to here, so we can see that it's donating a proton. Okay, and this is also in the reverse reaction. This is donating a proton to this species here to make the phenol. Okay, all right. So this would also be an acid. Okay, structurally, what we can see by this other acid is that it has a couple of electronegative atoms. Okay, and that's also present here as well. And electronegative atoms, they enhance acidity, right? Okay, all right, so we're going to say that this would be the strong acid, and this would be the weak acid. Okay, the strong base is the conjugate base of the weak acid, which is here, so this is the strong base. And remember that strong and weak are always on the same side of the equation. There's our weak base. Okay, if we had to estimate the pKa, remember that lower pKa means stronger acid, right? So we say that pKa here is a number less than 10. Okay, we don't really know quantitatively what that is, but we would estimate that its value would be something below 10. Okay, all right, let's look at this one. We're going to answer the questions concerning the bonding, the shapes, and the hybridization in the molecule below. Notice that it doesn't have any formal charges, but there actually are some formal charges present. If you look at this, all the carbons have 4 bonds, the oxygen has 2 bonds, this nitrogen has 3 bonds and a lone pair. So these aren't charged, but this nitrogen here has 4 bonds, so it's not normal. Okay, so charge at left nitrogen number 1 does have a charge. We're going to take 5 for the valence nitrogen. We're going to subtract 4 for the number of bonds, minus 0 lone pairs. It's plus 1. So we're going to put a plus right there, and that's the only charge on the molecule. So that's the charge on this molecule is plus 1. How many pi bonds are in this molecule? Well, remember, each double bond is a single bond and a pi bond. Okay, so we're going to look at all the double bonds, and they're going to each be a single bond and a pi bond. So we have 1 pi bond there, 1 pi bond there, and 1 pi bond there. So there are 3 pi bonds in this molecule. The electron pair geometry at nitrogen number 2 is trigonal planar. And it's sp2. We can tell that this is trigonal planar because there's a lone pair plus 2 atoms attached to the other nitrogen and carbon. Okay, all right, so that gives us the trigonal planar geometry. The only CH bond is right here, and it's overlapping s orbital of hydrogen. That's the only type of orbital that hydrogen has. And at C3, it looks like this is a trigonal planar carbon, so it's sp2. Remember that sigma bonds come from the s and p hybrids. And the X there corresponds to the geometry at the carbon of interest. Okay, all right, the CC sigma bond, there's the only CC bond right there. There's a sigma bond and a pi bond. This is asking for the sigma bond. Okay, so carbon 3 is trigonal planar and sp2. Carbon number 4 is linear and sp. So we're going to put sp for this one. Okay, the CC pi bond results from overlap of a p orbital with a p orbital. When we're looking at pi bonds in organic chemistry, these almost always come from p orbitals. Okay, the only exception we'll see is when we have the occasional things with d orbitals. Okay, what's the delta H for the following reaction? We're going to calculate that from the heat of combustion, and remember that delta H equals the heat of combustion of the products minus the reactants. Okay, so this is a balanced equation. Remember that it takes 3 of these to make a cyclohexane. So if we want to calculate delta H would be basically 3,900 minus 1,400 times 3. That's 4,200. And our delta H would be negative 300 kilojoules per mole. All right, another thing that this question is asking us to do is to rationalize why the reaction might be exothermic or endothermic based on favorable structural changes. And the one thing you can see here is that the product has only sigma bonds. And sigma bonds are stronger than pi bonds. So that would account for why that is a more favorable compound. Okay, all right, so when we convert the pi bonds to the sigma bonds, that's a very favorable process. We're not really introducing any angle strain or anything because cyclohexane, the angle strain is pretty minimal, right? So we're not going to be doing that. So yeah, so the only thing that's really happening is that 3 of the sigma bonds are converting to CC pi bonds, okay? Sorry, 3 of the CC pi bonds are converting to 3 of the CC sigma bonds, 3 additional CC sigma bonds. Okay, we're going to determine whether each transformation is oxidation, reduction, or neither. Okay, so the first thing to remember is bond line diagrams. They're not necessarily your friends in this type of equation. Okay, so if we look at the starting material, we're going to pretend that the hydrogen is an H+, the chlorine is a minus. The only other bonds to the carbon of interest here are other CC bonds, so we don't count them. So this is going to be carbon 0. All right. This is going now to produce the product, and again, H+ is going to be that. Single bond to nitrogen or oxygen is a negative, and so it's a plus and a minus. So this carbon here is essentially a carbon 0. Okay, so carbon 0 is going to carbon 0. We're going to refer to this as being a neither. This is not a redox reaction. This is a substitution reaction, a type of reaction that we'll encounter later in the class. Okay, all right, this one. Okay, so remember that we have hydrogens here that are not being shown in the bond line diagrams, but if those are H pluses, that means each of these carbons is -1. So the sum of all carbons that are changing is carbon 2-. Okay, this is going to produce 2 carbons that kind of look alike, H+ and Cl-. So this is 0 here. This is carbon 0, so the sum of these is 0. Okay, so when we go carbon -2 to carbon 0, okay, we are actually increasing the oxidation number. -2 to 0 is an increase, therefore this is an oxidation. Okay, and let's look at this one. The chlorine is converting to a lithium. Okay, so in the right-hand side, this basically looks like the one above there, same compound. This is carbon 0. Okay, the only carbon that changes is the one with the lithium. Lithium is on the left side of the periodic table, so it's very non-electronegative. We call that electropositive. So this would be carbon 2-. So if carbon 0 goes to carbon 2-, that's actually a lowering of the oxidation number, and we would refer to this one as a reduction. Okay, all right, so really it all depends on the way the bond dipole goes, right? So that's, chlorine is giving it a partial plus, and that's why we put chlorine minus, whereas lithium, carbon is more electronegative than lithium, so that's why we give lithium a plus and carbon, well, it's going to adopt the whatever the hydrogen was too, but we have to consider that. But both the H plus and the lithium plus, both the hydrogen and lithium take the dipole in the same direction. Okay, all right. All right, so let's look at these two. We want to determine what these two species look like in 3 dimensions. Okay, all right, so let's assume that T-butyl is always going to be equatorial because it's so large. Okay, so if we had to draw that, put T-butyl there, nothing on this carbon. This methyl is up. This methyl is down. Okay, if we don't see the methyls all that well because they're equatorial, just remember that they're the opposite of what the hydrogens are. Okay, and this one, okay, T-butyls we're going to keep at the same place. Methyl, we're going to put it down. Here we're going to put methyl up. And we're going to say that this is going to be more stable, right? Because both methyls are equatorial. Okay, and here we have, and the one on the right, both of the methyls will be axial. And remember, the T-butyl is so large that we consider these to be conformationally locked systems. So we don't even consider any sort of ring flips here because T-butyl is so large. Here, in this next one, what we want to do is identify the Gauche interactions. And there's one there between methyl and ethyl. And here's one between ethyl and isopropyl. We're going to choose this one here as being more stable because basically the isopropyl is bigger than methyl. Okay, thus the methyl isopropyl Gauche interaction is less severe than the methyl ethyl Gauche interaction is less severe than the ethyl isopropyl interaction. Okay, and isopropyl is larger than both methyl or ethyl. Okay, all right. And this other one, we're going to choose this one as likely being the more stable one. Okay, and this is because angle strain in a 3-membered ring is more severe than in a 4-membered ring. Okay, all right, and I guess if you want to argue that maybe the 6-membered ring was so stable, you might want to choose the one on the left, but remember that the energy difference between cyclopropyl and cyclobutyl was a lot bigger or a lot more severe destabilizing for the cyclopropyl than when you compared a cyclopentane and a cyclohexane. So I'm going to say that the one on the right is probably going to be more stable. Okay, we're going to draw each species. We're going to draw 3-methylhexane in the most stable conformation, citing the C3-C4 bond. Let's look at that compound. All right, here's 3-methylhexane. This is C3-C4 right here. We're not necessarily going to draw the right answer the first time we do this, but let's just draw a couple of things here first. Okay, so if we do if this front one is C3, it's going to have a methyl, an ethyl, and hydrogen. Okay, and the back one is going to have hydrogen, hydrogen, and ethyl, right? Okay, there's ethyl at C4, and here is ethyl at C3. Okay, all right. We need to rotate them. Let's make sure that we go through all of the rotations. And I'm just going to rotate the back one by 120 degrees at a time. Keep the front one the constant. There we go. And let's just say that we're going to probably choose this one as being the most stable. And we're going to choose this because ethyl larger than methyl, not by much, but enough so that we'd probably see that that conformation was more stable. So this would be our most serious Gauche interaction here. This would be a little bit more severe because it's an ethyl with an ethyl, and this one just downright bad here because it's got 2 Gauche interactions. Okay, trans isomer of 1-chloro, 3-ethyl cyclohexane in the most stable conformation. Okay, so that would be this compound. Okay, to do this, you'd have to consider both isomers, or both ring flip conformers. So let's put chlorine up, ethyl down. Let's ring flip this. Okay, and when we do this, get chlorine now equatorial and ethyl axial. This statement here, ethyl is bigger than chlorine, tells us that this one is going to be more stable. Because the larger group, ethyl, is equatorial. Okay, all right, and in this last one, okay, we're going to just finish out the chair structure in these conformationally very rigid molecules here. Okay, so here, let's just go ahead and put the substituents at the places where they're needed. Okay, so right at this carbon here, a chlorine goes here. So what So chlorine needs to be up. Axial is definitely up, so this is what we have here. Methyl at this carbon needs to be down. So you can tell that axial is up, so we'll put a hydrogen up and the methyl down right there. At this one, the ethyl should be down, and you can see obviously that down is axial. Here, the fluorine should be down. Obviously, hydrogen is, or up is the axial direction, so the fluorine should be down, and that would be our product there. These trans-Decalin systems are conformationally immobile or conformationally locked, so we wouldn't need to worry about any sort of ring flip isomer there. Here we're going to finish out by fusing additional 6-membered rings onto things. Okay, so we're going to add the 6-membered ring to these carbons here. Let's look at the hydrogen. Here is going to be up and axial. This hydrogen is going to be down and axial. So we're going to fuse another chair onto this one. So that would be, we'll call this the C ring here. And we now need to add in the D ring. So we have a hydrogen that's axial here, and a hydrogen that's equatorial here. So if we look at what we have here, something like that would be how we would finish the ring system out for the D ring. So the 6-membered rings that we add should be chairs, and we should keep the A and B as the conformationally locked trans-Decalin system, and we're going to add the other structures where the substituents need to be. Okay, all right, so that's